Hello there, and welcome to the Sleeping Physicist. If you're someone who likes to unwind by thinking about atoms, light, and the quiet structure of the universe, you're in the right place. Tonight, we'll let our attention drift gently into real quantum physics and real discoveries. Some of what we'll explore may sound unfamiliar at first, but all of it is grounded in how nature actually behaves. And if you enjoy these slow, careful explorations, you're always welcome to like and subscribe. But for now, settle in. Let your body rest, let your thoughts soften, and let's begin. What is a molecule actually made of according to quantum physics? When we first learn about molecules, they're often presented as tiny objects, like little clusters of beads glued together, each bead representing an atom with a definite surface and boundary. In everyday life, this makes sense because molecules behave as if they are solid and stable, forming the air we breathe, the water we drink, and the ground beneath our feet. When you hold a glass or smell a flower, it feels natural to imagine countless microscopic pieces quietly sitting in place, each one small but solid in its own way. But as soon as we begin to look more closely, this comforting picture starts to dissolve. Even the smallest molecule is mostly empty space, and the parts we imagine as solid have no sharp edges at all. There is no tiny shell you could touch, no miniature object that stays still long enough to point to. What we call a molecule does not behave like a shrunken version of a familiar thing, because at this scale, nature follows different rules. This is not a failure of imagination, but a clue. The solidity we experience does not come from hard boundaries, but from interactions, constraints, and patterns that repeat with extraordinary reliability. The molecule appears solid to us, not because it is made of solid stuff, but because its internal structure resists change in a very precise way. Resistance has nothing to do with stiffness or rigidity in the everyday sense, and everything to do with how energy, motion, and probability arrange themselves at the smallest scales. Once this shift begins to settle in, it becomes clear that to understand what a molecule is made of, we have to let go of the idea of tiny objects sitting quietly in space. Instead, we begin to follow something more subtle and more reliable: the way nature organizes motion so that certain arrangements last. When scientists first tried to explain what replaces the idea of a solid molecule, they turned to atoms as the next layer down. Atoms were imagined as the smallest stable units of matter, each one containing a dense central nucleus surrounded by electrons, a bit like a tiny solar system. In this picture, molecules form when atoms come close enough for their outer parts to interact, linking together while still remaining distinct. This classical image is useful because it introduces real components that can be named and studied. The nucleus contains almost all the mass, made of protons and neutrons tightly packed into a region far smaller than the atom itself. Electrons occupy the surrounding space, carrying negative charge and determining how atoms influence one another. When atoms approach, it is these electrons that meet first, long before the nuclei come anywhere near contact. At this level, a molecule begins to look less like a solid object and more like a structured arrangement. The atoms do not fuse into a single lump. They keep their identities, held in place by electrical forces between positively charged nuclei and negatively charged electrons. The molecule exists because these forces balance in a way that neither pulls everything apart nor lets it collapse inward. Yet even here, something important is missing. If electrons were simply tiny particles circling nuclei like planets, there would be no clear reason for molecules to be stable at all. Classical physics predicts that moving charged particles should radiate energy and spiral inward, destroying the very structures we observe. The fact that molecules persist, holding their shapes and energies with remarkable consistency, tells us that the classical picture is only a stepping stone, not the final explanation. This realization gently forces us forward toward a deeper description of electrons themselves, and toward the rules that actually allow atoms to combine and remain whole. The deeper scientists looked into this classical picture, the more its limits became impossible to ignore. If electrons truly behaved like tiny charge balls moving along definite paths, molecules should be fragile and short-lived. The electrical attraction between electrons and nuclei would pull everything inward, while the motion of those electrons would continuously leak energy away. Nothing would stay arranged for long. But real molecules do not behave this way. They form, they persist, and they return to the same structures again and again with astonishing precision. A water molecule today has the same internal arrangement as a water molecule formed billions of years ago. This kind of reliability cannot come from particles endlessly losing energy and spiraling into collapse. The problem is not with the idea of charge or force, but with the assumption that matter at small scales behaves like matter at large ones. Classical particles have positions and velocities that can be known at the same time, and their motion unfolds smoothly through space. At the scale of molecules, nature refuses to cooperate with that expectation. The stability we observe cannot emerge from objects that follow classical rules. This failure turns out to be profoundly useful. It tells us that molecular structure is not enforced by rigidity, but by something more subtle. Stability arises not because parts are locked in place, but because certain motions are allowed and others are forbidden. Energy does not slide continuously downward. It comes in steps, and those steps matter. Once this becomes clear, the question shifts. Instead of asking how tiny particles hold still, we begin asking how motion itself is constrained. And to answer that, electrons can no longer be treated as little objects at all. They must be understood in a fundamentally different way. What replaces the classical electron is not another kind of tiny particle, but a different description of how matter exists at small scales. In quantum physics, an electron is not defined by a precise location moving along a path. Instead, it is described by a spread of possibility, a wave-like presence that occupies space all at once. This wave is not something the electron rides on, it is the electron itself. This change solves the problem of collapse immediately. A wave does not spiral inward the way a particle does. It naturally settles into stable patterns. Just as a plucked string settles into standing vibrations, these patterns do not lose energy continuously. They exist only at specific allowed energies, and once formed, they persist unless something actively disturbs them. The electron wave surrounding a nucleus forms a stable arrangement because only certain wave patterns fit. Others simply cannot exist. The atom becomes stable not because the electron is held in place, but because its wave cannot adopt any shape that would lead to collapse. The rules of quantum physics quietly prevent it. This is a very different kind of substance than anything we encounter in daily life. The electron is not smeared out because we are ignorant of its position. It is spread out because that is what it means to be an electron. Its presence is defined by likelihood, not certainty, and by structure rather than trajectory. Once electrons are understood this way, molecules begin to look less like collections of objects and more like shared wave patterns. And it is within those shared patterns that the true material of a molecule begins to take shape. Once electrons are understood as waves, the space around an atom changes meaning entirely. Instead of paths or tracks, what forms are stable patterns in which the electron wave can exist. These patterns are called orbitals, but the name can be misleading. Nothing is orbiting, nothing is circling. An orbital is simply a three-dimensional shape that describes where the electron is likely to be found. A helpful way to picture this is to imagine a quiet room filled with mist. The mist is denser in some regions and thinner in others. You cannot point to a single droplet and call it the electron. The electron is the entire pattern of density itself. Where the mist is thick, the electron is more likely to interact. Where it thins out, interaction is less likely. The shape of that mist is fixed by quantum rules, not by motion. These shapes are not chosen freely. Each one corresponds to a specific energy, and only certain shapes are allowed. This is why atoms have distinct chemical behaviors. The orbitals define how electrons are distributed in space, which determines how atoms can approach one another and what kinds of connections they can form. Importantly, these probability patterns are not vague or unstable. They are sharply defined by mathematics and confirmed by experiment. The electron does not wander randomly through all space. Its presence is constrained into a precise form that repeats every time the same conditions are met. With this picture in place, a molecule begins to emerge not as atoms touching, but as orbitals beginning to overlap. The substance of a molecule is no longer found in tiny objects meeting at boundaries. but in the way these probability patterns combine and reshape one another. As two atoms drift closer, nothing snaps together and nothing collides. What happens instead is quieter and more gradual. The probability patterns that define each atom's electrons begin to extend into the same region of space. The mist, like shapes that once belonged clearly to one atom or the other, start to overlap. This overlap is not a secondary effect. It is the moment where a molecule begins to exist. The electrons are no longer confined to one nucleus alone. Their wave patterns now feel the presence of more than one positive center, and the shape of those patterns adjusts in response. Space itself becomes shared. You can think of this like two gently humming tones in a room. When they are far apart, each sound is distinct. As they move closer, the air between them carries both vibrations at once. New patterns of resonance appear, not owned by either source alone. In the same way, overlapping orbitals create regions where electrons belong to the system as a whole rather than to a single atom. This overlap changes energy. Some arrangements lower the total energy of the electrons, making the combined system more stable than the separated atoms. Others raise the energy and quickly dissolve. Nature quietly selects the arrangements that cost less energy, because those are the ones that last. At this point, the molecule is no longer a collection of atoms held together by force alone. It is a single quantum system, defined by shared electron patterns that span multiple nuclei. The substance of the molecule is beginning to reveal itself as something collective rather than assembled. As orbital overlap deepens, the system crosses a quiet threshold. The electron patterns no longer belong to individual atoms at all. They reorganize into new shapes that extend across the entire group of nuclei. This is the formation of molecular orbitals, and it marks the point where a molecule becomes a single quantum object rather than a temporary association. The key shift here is not the addition of force, but a change in identity. The electrons no longer belong to one atom or another. They exist in states defined by the molecule as a whole. Their probability patterns stretch from one nucleus to the next, sometimes evenly, sometimes with subtle imbalances, but always as part of a single, unified OT structure. The molecule is not held together by electrons shuttling back and forth between atoms. It persists because the lowest energy states available to the electrons are states that naturally include all the nuclei at once. A useful way to understand this is to imagine two basins of water connected by a shallow channel. When separated, the water in each basin settles independently. Once connected, the water level equalizes and becomes one continuous surface. The water has not moved because it was pushed, but because the combined system allows a lower, more stable arrangement. In the same way, molecular orbitals form because the shared quantum state allows electrons to occupy a configuration that is more stable than any isolated alternative. These molecular orbitals are not optional. Given the same atoms and the same conditions, they always form in the same way. This is why chemistry is reliable. The shapes and energies of molecular orbitals are fixed by quantum laws, not by chance or history. Every molecule of oxygen, every molecule of water, shares the same internal quantum structure because the rules that shape those orbitals never vary. It becomes clear that what we call a chemical bond is not a physical tether. It is a consequence of which quantum states are allowed to exist. Electrons occupy the states that minimize the total energy of the system, and those states happen to involve sharing space between nuclei. The bond is not something added afterward. It is simply the name we give to this shared state itself. Once molecular orbitals form, the electrons no longer serve one nucleus or another. They serve the molecule. Their presence stabilizes the arrangement of nuclei by distributing negative charge in a way that balances repulsion and attraction across the whole structure. The molecule persists because there is no simpler configuration available to it. This understanding quietly replaces the idea of matter as assembled pieces. In the formation of molecular orbitals from shared quantum states, a molecule reveals itself as a pattern that nature prefers, a pattern made not of solid parts, but of standing waves of probability that hold their shape simply because nothing more stable exists. As molecular orbitals form, they do not all contribute to stability in the same way. Some arrangements endure, while others fade almost immediately. The difference between them is subtle but decisive, and it determines whether atoms remain together or drift apart again. When atomic electron waves combine, they can merge in ways that reinforce one another. In these arrangements, the shared electron presence becomes denser in the region between the nuclei. This concentration lowers the total energy of the system. The positively charged nuclei respond by settling into positions where this shared distribution remains intact. Nothing is being pulled together, like objects tied with a cord. The stability arises because the entire configuration is energetically quieter than separation. Other combinations behave differently. The electron waves interfere in a way that removes probability from the space between the nuclei, pushing electron presence outward instead. These arrangements raise the system's energy. They are allowed briefly, but they do not last. Without shared electron density to stabilize the nuclei, the configuration dissolves and the atoms move on. This distinction explains why chemistry is selective. Not every atom bonds with every other atom, and not every close encounter produces a molecule. Only those shared electron patterns that lower the total energy can persist. The rest vanish, not because something breaks, but because nothing stable has formed. What we call a chemical bond is simply the name we give to one of these energy-lowering arrangements. It is not a physical tether or a force added after the fact. It is the shared quantum state itself. When electrons are permitted to exist in a way that stabilizes multiple nuclei at once, the bond exists. When they are not, it does not. This also explains why bonds have characteristic strengths. Some shared states lower energy by a great deal, producing molecules that are difficult to separate. Others lower it only slightly, creating fragile structures that break easily. Bond strength is not about how hard something pulls. It is about how much more stable the bonded arrangement is compared to separation. As electrons occupy these allowed states, they do so in an orderly sequence. Lower energy arrangements fill first, while higher energy ones remain empty unless energy is supplied from outside, such as heat or light. This quiet ordering determines how many bonds form and how they behave. Seen this way, a molecule is not a collection of parts clinging together. It is a balance of allowed and forbidden possibilities, where stability emerges naturally, whenever electrons are permitted to share space in a way that lowers the total energy of the whole. As shared electron states sort themselves into stable and unstable arrangements, a deeper principle quietly governs everything that follows. The formation of a molecule is guided by energy, not as something dramatic or forceful, but as a gentle preference. Systems in nature tend to move toward configurations that require less energy to maintain, and molecules are no exception. When atoms approach one another, there are many possible ways their electrons and nuclei could arrange themselves. Most of these possibilities never last. They correspond to higher energy states that nature does not linger in. Instead, the system shifts, almost effortlessly, toward arrangements where the total energy is lower. This lowering does not require intention or direction. It happens because lower energy states are simply more available to exist. You can think of this like a shallow landscape of hills and valleys. A marble placed on this surface does not need to know where to go. It naturally settles into the nearest low point, because that is where motion ceases. In the same way, electrons and nuclei rearrange until no further energy can be easily released. The molecule forms when the system reaches one of these quiet valleys. What matters is not just the energy of the electrons or the nuclei alone, but the energy of the entire system taken together. As electrons spread across multiple nuclei in shared states, their energy decreases. At the same time, the repulsion between positively charged nuclei increases as they draw closer. A stable molecule exists precisely at the balance point where these opposing contributions settle into the lowest possible total. This balance explains why molecules have specific bond lengths. The nuclei do not drift endlessly closer, nor do they remain far apart. They settle at a distance where the combined energy of electron distribution and nuclear interaction reaches a minimum. Any movement away from that distance would increase energy, making the arrangement less stable. It also explains why molecular formation releases energy. When a molecule forms from separate atoms, the final shared state has lower energy than the initial separated state. The excess energy must go somewhere, often released as heat or light. This release is not a side effect, it is the signature that the system has found a more stable configuration. Importantly, this process does not require an external organizer. There is no instruction telling atoms how to bond. The rules of quantum physics define which states are allowed, and energy minimization quietly selects among them. Given enough time and the right conditions, the system inevitably finds its way to stability. Seen through this lens, a molecule is not built piece by piece, it is discovered by the system itself. Out of countless possible arrangements, the one that costs the least energy is the one that remains. The molecule is that remainder, a stable pattern that persists because nothing simpler or quieter is available. In this way, molecular matter is not imposed on the universe. It emerges naturally, guided by the unremarkable but relentless tendency of physical systems to settle into the states that ask the least of them. Once energy has settled into its lowest arrangement, something subtle but important becomes clear. The molecule does not consist of tiny points or rigid parts. What actually fills the space of a molecule is electron density, a continuous distribution of probability that occupies volume and has shape. This electron density is not a shadow or a mathematical trick. It is the closest thing a molecule has to physical substance. Instead of imagining electrons as objects moving inside a structure, it is more accurate to imagine the structure itself as made from where electrons are likely to be. The molecule exists where this probability is concentrated. Where electron density is high, the molecule resists intrusion. Where it is low, other particles may pass more easily. The solidity we experience is a direct result of these density patterns interacting with one another. This is why molecules have size. Their boundaries are not sharp edges, but gradual fall-offs in electron probability. As you move away from a molecule, the electron density thins smoothly rather than stopping abruptly. There is no exact surface where the molecule ends. There is only a region where interactions become less likely. You can picture this like a softly glowing cloud whose brightness fades with distance. The glow marks where the molecule effectively is. Two such clouds cannot easily overlap, because doing so would force electrons into higher energy states that the system resists. This resistance is what your hand feels as solidity when you touch an object made of countless overlapping molecular clouds. Electron density also explains why molecules can interact without ever touching in a classical sense. Chemical reactions, attractions, and repulsions all occur through changes in these probability distributions. When molecules approach one another, their electron clouds distort, repel, or rearrange, long before any nuclei come close. Matter communicates through these clouds. Importantly, this density is not static. It is stable, but alive with quantum motion. The electrons are not frozen in place. Their probability distributions persist even as individual measurements would reveal different outcomes each time. The molecule holds its shape not because nothing moves, but because the pattern itself is the stable feature. This view resolves a quiet contradiction. Molecules feel solid and definite, yet they are made mostly of empty space. The resolution is that solidity does not require filled space. It requires stable patterns that resist change. Electron density provides that resistance through quantum rules, not material hardness. Seen this way, a molecule is not built from particles stacked together. It is built from a field of likelihood, shaped by energy constraints and shared across nuclei. The true material of the molecule is this field itself, an organized presence that occupies space, defines boundaries, and persists through time without ever becoming a solid thing in the classical sense. What we call matter, at the molecular level, is not substance in the old meaning of the word. It is structure without rigidity, presence without solidity, a quiet architecture made entirely from the way probability settles when nature finds a stable arrangement. Once a molecule is understood as a pattern of electron density rather than a collection of solid parts, an obvious question follows naturally. If molecules are clouds of probability, why do they have such precise shapes? Why does water always bend at the same angle? Why do some molecules form straight lines while others twist into complex geometries? The answer again lies in how electron density arranges itself to minimize energy. Electron clouds repel one another, because placing electrons too close together forces them into higher energy states. As a result, the shared electron density within a molecule spreads out in space in a way that keeps these repulsions as low as possible while still stabilizing the nuclei. You can imagine this as several softly inflated balloons tied together at a central point. Each balloon pushes gently against the others, not because it wants space, but because overlapping would cost energy. The final arrangement is the one where the balloons are as far apart as possible while remaining connected. Molecular shapes emerge from the same quiet negotiation. The orbitals that make up a molecule are not shapeless. Each one has a specific geometry determined by quantum rules. When multiple orbitals are occupied, their shapes must coexist in the same space. The molecule settles into a geometry where these shapes interfere with one another as little as possible. The angles between bonds are not chosen arbitrarily. They are the result of this spatial compromise. This is why molecular geometry is so consistent. Given the same atoms and the same number of electrons, the same shapes always emerge. A carbon atom bonded to 4 others will always arrange itself in the same 3-dimensional pattern, because that pattern represents the lowest energy way for its electron density to spread out. Chemistry inherits its reliability directly from quantum mechanics. These shapes are not frozen sculptures. They are average arrangements that persist over time. The electron density is constantly in motion, but the overall pattern remains stable. The molecule vibrates, bends slightly and flexes, yet always returns to its characteristic geometry, because any large deviation would raise the system's energy. Molecular shape also determines how molecules interact with one another. Because electron density fills space in specific ways, molecules can fit together or repel one another depending on their geometry. This is why shape matters in biology, why enzymes recognize specific molecules, and why the same atoms arranged differently can behave like entirely different substances. What appears to us as form is, at the quantum level, a solution to a problem. How can electrons be shared among nuclei while avoiding unnecessary energy cost? The shape of the molecule is the answer nature finds. Seen this way, geometry is not imposed from the outside. It is not a blueprint stamped onto matter. It emerges from the quiet requirement that electron density arrange itself in the least demanding way possible. Molecular shape is simply energy expressing itself in space. So when we look at a molecular diagram with neat angles and clean lines, we are not seeing an abstract model. We are seeing a shadow of a real quantum arrangement, a stable pattern of probability that holds its form because nothing simpler can replace it. As precise as molecular shapes are, there is something even more remarkable beneath them. Nothing inside a molecule is trying to fall inward, and nothing is propped up to keep it from doing so. The reason a molecule does not collapse into a dense knot of charge is not balance in the classical sense, but constraint. Quantum physics quietly forbids certain kinds of motion, and those prohibitions are what keep matter extended in space. Electrons cannot simply pile on top of one another, or sink endlessly toward a nucleus. Their wave nature restricts how tightly they can be confined. Squeezing an electron's probability distribution into a smaller region of space raises its energy. At some point, that cost becomes too high. The molecule settles into a size and structure where further compression is no longer allowed without adding energy from the outside. This is not resistance in the way a solid resists being crushed. It is a limit built into the rules themselves. The electron density spreads out because it must. Any attempt to force it into a smaller volume would require placing electrons into higher energy states that the system naturally avoids. There is also a deeper constraint at work. Electrons are not interchangeable occupants of the same state. Each allowed quantum state can only be filled in very specific ways. Once the lowest energy states are occupied, additional electrons must occupy different, higher energy arrangements. This layering of states creates an internal structure that prevents collapse automatically. The molecule is stable not because something holds it open, but because there is nowhere lower for its electrons to go. You can imagine this like a stack of cushions on a floor. The lowest cushion settles first. Any additional cushion must sit on top, even if gravity would prefer everything to compress downward. The structure builds upward, not by choice, But because the rules leave no alternative, molecular structure forms in the same inevitable way. These constraints also explain why matter has volume. Even though atoms and molecules are mostly empty space, they occupy definite regions because their electron states cannot all occupy the same place or energy. Space is claimed not by substance but by restriction. The molecule takes up room because quantum rules prevent it from being smaller. This also explains why matter is stable over time. Nothing inside a molecule is decaying toward a lower configuration, because the lowest configuration has already been reached. The molecule exists in a state where all allowed motions are accounted for. Without an external disturbance, there is simply nowhere for it to go. What feels like solidity and permanence emerges from these invisible limits. The molecule persists not because it is rigid, but because its internal possibilities are exhausted. It has settled into a pattern that cannot simplify further without breaking the rules of quantum physics. Seen this way, matter is not fragile. It is quietly locked into place by the same laws that allow it to exist at all. Molecules endure not through strength, but through constraint, through a structure of permissions and prohibitions that holds them open in space and steady in time. The everyday stability of the world is built from these silent restrictions, rules so fundamental that they do not announce themselves, yet so reliable that entire planets can rest upon them. Even in its most stable form, a molecule is never truly still. Stability does not mean silence, it means motion that is carefully constrained. Within every molecule, the nuclei and the surrounding electron density are constantly moving, not freely, but in specific, allowed ways. These motions are not signs of instability. They are part of what it means for the molecule to exist. The nuclei within a molecule are held in place by shared electron density, but they are not fixed points. They oscillate around their preferred positions, moving closer together, and farther apart in a rhythmic way. This motion is called vibration, and it happens even at the lowest possible energy. The molecule cannot eliminate this motion entirely, because quantum physics does not allow perfect stillness. These vibrations occur in discrete patterns. A molecule cannot vibrate in just any way. Only certain motions are permitted, each with a specific energy. The simplest vibration resembles a gentle stretching and compressing of bonds, like a spring that can expand and contract, but only at particular frequencies. More complex molecules support richer patterns, with bending, twisting, and coordinated motions across the structure. Rotation adds another layer. Entire molecules can rotate in space, again, not continuously, but in quantized steps. The molecule does not spin at arbitrary speeds. It occupies specific rotational states, each one corresponding to a distinct amount of energy. Transitions between these states involve precise exchanges of energy, often in the form of absorbed or emitted radiation. These motions are not disturbances layered on top of a solid structure. They are built into the molecule's identity. The allowed vibrations and rotations are determined by the same quantum rules that defined the molecule's shape and stability in the first place. A molecule is not a static object with motion added later. It is a dynamic pattern whose motion is part of its definition. This is why molecules interact with light in such specific ways. When a molecule absorbs infrared radiation, it is often exciting one of these vibrational modes. When it absorbs microwave radiation, it may be changing its rotational state. Each molecule has a unique spectrum because each has a unique set of allowed motions. The way a molecule moves is a direct fingerprint of how it is built. You can think of this like a musical instrument. A violin string does not produce every possible sound. Its length, tension, and material allow only certain notes. In the same way, a molecule supports only certain motions set by its mass distribution and electron structure. The molecule resonates with the universe in very specific ways. These internal motions also explain why molecules are flexible without falling apart. Bonds stretch and bend, but only within limits. The energy landscape guides the motion back toward the preferred configuration. The molecule explores its allowed possibilities continuously, yet remains recognizable because the lowest energy arrangement still dominates. At ordinary temperatures, molecules are already vibrating and rotating. Heat does not create motion from nothing, it simply shifts the population of molecules into higher allowed states. The structure remains intact until enough energy is added to push the system into states that no longer support bonding. Seen from this perspective, a molecule is not a frozen arrangement of probability. It is a living pattern of motion, constrained, repeatable, and remarkably precise. Its vibrations and rotations are not imperfections. They are the quiet evidence that quantum rules are still at work, even in the calm persistence of ordinary matter. With all this motion, spread, and probability at the heart of a molecule, it might seem surprising that the world feels as solid and definite as it does. Tables do not shimmer, walls do not blur. Molecules appear to have fixed positions and reliable boundaries. This apparent contradiction is resolved not by adding new structure, but by understanding what happens when quantum systems are observed and interact at large scales. A molecule on its own is described by probability patterns, but molecules are almost never alone. In everyday matter, countless molecules are packed together, constantly interacting with one another and with their surroundings. Each interaction acts like a kind of measurement, not in the sense of a conscious observer, but as a physical exchange of information. These interactions continually reinforce certain outcomes and suppress others. When a molecule interacts with its environment, many of its quantum possibilities become irrelevant. The delicate spread of probability narrows into outcomes that are stable enough to persist through repeated interactions. The molecule does not lose its quantum nature. Instead, its quantum behavior becomes constrained into patterns that behave predictably at human scales. This is why molecules appear to have positions, not because their electrons suddenly become classical particles, but because constant interaction with surrounding molecules locks certain properties into place. Position becomes well defined, because any large deviation would immediately interact with the environment and be corrected. The molecule is not pinned, it is stabilized. Solidity arises from this collective behavior. When you press your hand against a surface, the electron density of the molecules in your skin encounters the electron density of the molecules in the object. These clouds cannot overlap freely. Doing so would require forcing electrons into higher energy states, which the system strongly resists. That resistance is what you feel as a solid surface. At no point do molecules actually touch in the classical sense. Nuclei remain far apart. What interacts are probability distributions, shaped by quantum rules and reinforced by constant measurement through interaction. The solidity of matter is an emergent effect, arising from vast numbers of quantum systems behaving together in constrained ways. Observation also explains why molecules appear stable over time. While individual quantum events are probabilistic, the average behavior of trillions of particles becomes extremely reliable. The randomness washes out, leaving behind patterns that are effectively fixed. A molecule behaves the same way every time, because deviations are statistically overwhelmed. This does not mean the quantum description disappears. It remains essential for explaining why the solidity exists at all. Classical physics can describe how objects move once solidity is present, but it cannot explain why that solidity emerges. The explanation lives entirely in the quantum structure of matter and the way observation through interaction shapes outcomes. In this way, the everyday world is not separate from the quantum world. It is built from it. The firmness of a chair, the resistance of the floor, the defined shape of your own body, all arise from quantum probability made stable through interaction and repetition. A molecule appears solid, not because it is solid in itself, but because its quantum structure is continually affirmed by the world around it. What feels definite is the result of countless quiet confirmations, happening so quickly and so consistently that uncertainty never has a chance to show itself. The solidity we trust is not a denial of quantum reality. It is its most familiar expression, scaled up through number interaction and time until probability feels like certainty and patterns feel like things. When all of these pieces are allowed to settle together, a quiet picture comes into focus. A molecule is not an object in the traditional sense. It is not a miniature thing with parts arranged inside it. According to quantum physics, a molecule is a stable pattern, a self-sustaining arrangement of probabilities, energies, and constraints that persists because nothing simpler can replace it. At its deepest level, a molecule is defined by the quantum states its electrons are allowed to occupy. These states determine how electron density spreads through space, how nuclei are held at specific distances, how the structure vibrates and rotates, and how it interacts with light and other matter. The molecule exists wherever these states exist. There is no additional substance beneath them. This means a molecule is not made of electrons and nuclei in the way a wall is made of bricks. It is made of relationships. The electrons are defined by their shared states. The nuclei are defined by how those states distribute charge around them. The shape, size, and stability of the molecule emerge from the way these relationships fit together under quantum rules. You can think of it like a standing wave on a calm surface of water. The wave is real. It has shape, energy, and persistence, but it is not a separate object floating on the water. It is a pattern the water itself is allowed to form. In the same way, a molecule is a standing pattern in the underlying quantum fields of nature. It is matter behaving in one of the few stable ways available to it. This perspective dissolves the question of what the molecule is made of into something more subtle. It is made of allowed possibilities, of energy levels that can exist and others that cannot, of probability distributions that hold their form, because the rules leave them no alternative. The molecule is what remains after all instability has been ruled out. Seen this way, matter is not built from tiny solids. It is built from stability itself. Wherever quantum rules permit a pattern to persist, matter appears. Wherever they do not, nothing lasts. Molecules are simply the smallest structures where this persistence becomes recognizable and repeatable. This also explains why molecules feel so ordinary. They are not rare or fragile. They are the natural resting places of quantum systems. Given atoms, time, and the right conditions, molecules form because they are what quantum physics prefers. They are not accidents, they are outcomes. So when you hold a glass of water or breathe in the air around you, you are not surrounded by tiny objects bumping into one another. You are immersed in a vast collection of stable quantum patterns, each one quietly maintaining itself through rules that never sleep. A molecule, according to quantum physics, is not a thing hiding beneath appearances. It is the appearance itself, the calm, enduring shape that probability takes, when nature finds a way to remain. Once a molecule is understood as a stable quantum pattern, it becomes easier to see how the material world grows outward from this idea without ever abandoning it. Solids, liquids, gases, and even living tissue are not built from something fundamentally new. They are built from molecules interacting, aligning, and constraining one another in larger patterns that follow the same underlying rules. When molecules gather together, their electron density clouds begin to influence one another just as atomic orbitals once did. They do not merge into a single object, but they do adjust. Shared boundaries form where probability distributions press against one another, creating larger-scale structures that are still governed by energy minimization and quantum constraint. A solid is simply a configuration where these interactions lock molecules into repeating arrangements. A liquid allows them to slide while remaining close. A gas lets them wander more freely, still defined by the same quantum identities they always had. Nothing new is added at these larger scales. There is no moment where quantum physics hands control over to something else. The same principles that defined a molecule's shape and stability define how molecules stack, flow, and resist compression. The rigidity of a crystal, the softness of rubber, the fluidity of water all trace back to how molecular electron density responds to proximity and constraint. Even biological matter follows this rule. Proteins fold into specific shapes because their molecular structures permit certain arrangements and forbid others. DNA holds its form because its electron distributions favor a particular geometry. Life does not escape quantum physics. It rests entirely upon it, relying on molecular stability that is precise enough to be copied and flexible enough to change. At no point does matter become solid in the classical sense. It becomes reliable. Patterns repeat, interactions reinforce one another. The uncertainty that dominates small scales averages out across enormous numbers of molecules, producing behavior that feels fixed and dependable. What we call material reality is quantum behavior that has become statistically steady. This perspective quietly reshapes the idea of substance itself. Matter is not something added to space. It is what space does when quantum rules allow stable arrangements to persist within it. Molecules are the first clear expression of this persistence, the smallest units where stability becomes durable enough to build upon. So when you look around, nothing you see is truly made of things in the old sense. Everything is made of patterns that endure. Chairs, air, skin, stone, all are composed of molecular arrangements that have settled into states that can last long enough to be noticed. The universe does not assemble itself from pieces. It relaxes into forms. Molecules are among the earliest and most important of those forms. Quiet, solutions to the problem of how matter can exist at all. And in that sense, every molecule around you is doing the same simple thing. It is remaining, holding its shape, persisting gently in accordance with rules that do not demand effort or intention, only permission. What feels ordinary is, underneath, a continuous act of balance, maintained moment by moment by quantum laws that never stop applying, even when the world feels still. When all of this is allowed to come together, the idea of a molecule quietly changes character. It no longer feels like a puzzle made of smaller pieces, but like a calm answer to a deeper question. How can matter exist at all in a universe governed by motion, energy, and uncertainty? The molecule is one of nature's simplest and most successful answers. A molecule is not held together by force in the way our intuition suggests. It is held together by permission. Quantum physics allows certain arrangements of electrons and nuclei to exist at lower energy than others, and those arrangements persist. Everything we have described flows from that single fact: shared electron states, stable shapes, specific bond lengths, vibrations that never quite stop, boundaries that resist overlap. All of it emerges from the quiet filtering of what is allowed to remain. Seen this way, a molecule is not something assembled, it is something selected. Out of countless possible configurations, only a few are stable enough to last. Those few become the matter of the world. Nothing needs to push them into existence. Given time and the right conditions, they appear because they are the resting points of quantum behavior. This perspective also softens the boundary between matter and emptiness. Molecules are mostly space, yet they occupy volume. They are mostly motion, yet they persist. They are built from probabilities, yet they behave predictably. These are not contradictions. They are consequences of rules that operate quietly and consistently beneath everything we experience. What we call solidity is not hardness at the smallest scale. It is refusal. The refusal of electrons to share the same states. The refusal of probability patterns to compress without cost. The refusal of systems to move uphill in energy without being pushed. The world feels firm because quantum rules say no long before anything actually touches. Even permanence is revealed as something gentler than it appears. Molecules endure not because they are immutable, but because they are already as simple as they can be. Their stability is not frozen, it is satisfied. With no lower energy arrangement available, the molecule remains, moment after moment, through constant motion that never escapes its bounds. This understanding does not make the world feel abstract or distant. If anything, it makes it more intimate. Every breath, every surface, every familiar object is built from the same quiet logic. Patterns that found a way to stay. Structures that emerged not through effort, but through inevitability. The universe did not plan molecules. It allowed them. And because the rules are universal, this picture does not stop at the edges of chemistry. The same principles govern dust clouds, forming complex compounds in space, the folding of proteins in living cells, the materials beneath your feet, and the air around your face right now. Molecules are not a special case. They are a natural outcome. When quantum physics tells us what a molecule is made of, it does not point to a substance hidden beneath reality. It points to relationships, to energies settling, to motion constrained into form. The molecule is a pattern that learned how to last. There is something quietly calming in that idea. The world around you is not held together by tension or strain. It is held together by balance, by countless systems resting in states that ask very little of them. Matter persists, not because it must struggle to exist, but because existence in these forms is easy. So when you think of a molecule now, you do not need to imagine tiny balls glued together in the dark. You can imagine something softer and more precise, a shared cloud of likelihood, a standing wave of energy and charge, a shape that exists because the universe found no reason to undo it. And perhaps that is the most complete answer quantum physics offers. A molecule is made of what remains when instability has been removed. It is made of the allowed, of the lowest energy answers, of patterns that fit the rules so well they have nowhere else to go. In that sense, the molecules around you are not doing anything remarkable. They are simply continuing to be what they are, persisting quietly, holding their forms, letting the universe rest for a moment in structures that can last. And the calm familiarity of the world is built from that persistence, repeated unimaginably many times, until probability feels solid and motion feels still, and the deepest rules of nature become something you can hold, breathe, and live inside without ever noticing them at work.